Hello and welcome to Crystallography for Everyone. In this video, I am going to introduce this new series. I'm going to talk about why I think you should study crystallography, what kind of background I believe you should have coming in, and what our goals are, what type of topics we will be investigating. So on this slide, I show three different objects which I think are extremely important to us as humans and extremely relevant in crystallography. So on the left, we have DNA, the double helix structure of DNA. Very important to our lives as humans. I believe that if DNA was not structured in the way that it is, life would be unrecognizable. DNA happens to have a crystalline structure that has been understood through the concepts which we will cover in this class. On the upper right, we have some pharmaceutical drug. In the United States, every pharmaceutical that you take has gone through an extensive X-ray diffraction study to map out the atoms in the drug, so that when you take, for example, a painkiller, it kills your pain, but not you. So we're going to go through studying X-ray diffraction in this series. And in the bottom right, we have a field effect transistor. I believe this is one of the most important inventions in the history of mankind. It is the reason why you were able to watch this video. It's the reason why your cell phone works, or your personal computer. And it all works through the knowledge of crystals and the exploitation of their properties. So by the end of this series, we will be able to come back to this picture and understand in great detail the structure of all of the components of this transistor, and perhaps get an idea of why it works the way that it does. So our goals for this series. First off, we want to learn the language of crystals, some basic vocabulary, and the ground rules of how crystallography works in the field. These are things that anyone who works with crystals has to know. And this is going to allow us to have an intelligent conversation with each other, be able to communicate ideas about crystals. I think that's fairly crucial. We're going to almost immediately try and apply this knowledge. We're going to make physical predictions about the world through fairly simple theoretical concepts. And we're going to look at analysis techniques. We're going to have some real-world data that, using the language of crystals and these ground rules, that we're going to be able to really get an understanding for. Some ideas that are not immediately obvious. So some background that I think you should have. I think geometry and vectors are extremely important to understanding crystallography. They're going to come up in the first video of this series, first video where you're learning about crystals. So if these two terms are mysterious to you, I suggest that you head over to the Khan Academy and watch some of Sal Khan's videos. He's got an exhaustive library full of the theory and examples. And I think that reviewing them for a little while will give you a much more enriching experience throughout this series. Calculus and linear algebra are going to show up a bit. If you haven't taken them, or it's been a long time, don't worry, because I intend to step through these examples in great detail. I really don't like when my professors skip through the math, so I'm going to really strive to not do that. So I think that even if you haven't taken these classes, you will understand what I'm going to be working through, and In fact, if you go and take them in the future, you'll probably have a jump start on your classmates. And basic physics and chemistry will certainly help. I think that just the intuition that you get living in this world will probably be plenty. But if you've taken a high school chemistry class, you are all set. And for an example, something that usually scares a lot of students, I think, complex number theory is going to show up throughout this class. But I'm going to have several videos going through the basics of complex number theory and Euler's formula, and I think it will be very understandable. Here's a preliminary video list, fleshing out the goals a little bit. So we've got our introduction videos. These are our basic tools that we're going to use throughout the series. We're going to learn about lattices, unit cells, crystal planes, and how we index them, how we tell other scientists what plane we're referring to, and crystal directions, how we get around inside of crystals. We're going to look at concepts of symmetry. We're actually going to look at some different art pieces from artists like M.C. Escher. Believe it or not, we can learn quite a bit about crystallography from looking at M.C. Escher drawings. We're going to look at some basic applications almost immediately. We're going to jump in and make crystal density calculations that you can actually observe in real life. We're going to get remarkably close using some very simple models. We're going to visualize the crystal planes that we talked about earlier in the series, and we're going to make calculations of things like packing fraction. We're going to go into X-ray crystallography, which is one of the predominant techniques used to study crystals in the real world. If you find a chunk of some material, X-ray crystallography can tell you a huge amount about it. We're going to derive Bragg's law, which should be the basic equation which governs X-ray crystallography. We're going to use that to calculate crystal plane spacings. And we're going to calculate structure factors. Using all of this knowledge, we're going to look at some examples from research, from relatively recent work done in the field. And we're going to look at real-world X-ray diffraction data. We're going to analyze it and see if we can take X-ray diffraction data on an unknown crystal and determine its structure, determine what the crystal is made out of. So with that, I'm going to end this video, and in the next video we are going to jump straight into defining 1, 2, and 3D lattices. So I hope to see you there. Thank you.